Okay, thank you. And this is joint work with Dhruv Makwana, Thomas Sewell, Kayvan Memarian, Peter Sewell, and Neel Krishnaswami. So, in this talk, we're interested in system software verification. Why is that? Well, system software is important because, system software like operating systems or hypervisors is important because if it's broken, it affects the correctness and security of all the software that's running on top of it. So it's worth putting a lot of effort into making sure it's correct. Now, there's been a lot of work on this and lots of progress in recent years. And we now have things like verified hypervisors, verified operating systems, compilers, and lots of verification tools. Still, there remains a big gap between the typical verified system software project and conventional software development. For instance, verified system software is often software designed specifically for verification, often uses or assumes an idealized language semantics, and well, typically verification and maintenance remain very costly. Now, we're not going to sort of solve this problem here, but I'll tell you about an experiment that we're working on, an experiment in verification tool design that's trying to just sort of push a bit on this problem and make some progress. For instance, by using a more realistic language semantics than what previous verification tools have typically assumed. We want to target production systems code, and we're trying to reduce the cost of verification. And this verification tool is called CN, and it's a separation logic refinement type system for C. We've got a use case for this in mind, and that's the pKVM project. So what's pKVM? It's a hypervisor developed by Google for Android, and the idea is that it provides isolation between some untrusted Linux operating system and certain trusted guest virtual machines that have some access to confidential user data. It's written mostly in C with some ARM assembly, and it'll be included in Android 13. So it's a system that will be widely deployed, and it has this important role for the security of these devices. And so it makes sense to put a lot of effort into trying to make sure it works as intended. And so there's a Google-funded project to try proof that pKVM indeed provides these isolation guarantees. And now it's a big project across multiple sites, and there's many different sort of aspects involved in this verification. This is just looking at one aspect here, which is trying to prove the correctness of the pKVM C source code. And we want to do that using CN, so that's what CN is aimed at. And the way we see it, there's sort of two main challenges involved in doing this, for pKVM specifically, but also practical verification of production system software more generally. And the first one is just sort of handling production system software. That means dealing with the complexity of the semantics of C and the complexity of the code itself. So pKVM is written by a conventional development team, not specifically for verification. And so it has a lot of the typical difficult to reason about low-level idioms like pointer arithmetic, aliasing data structures, custom memory allocators, things like this. And then the second challenge we see is verification usability. So for just sort of making this proof feasible at all, and for later being able to maintain the proof as the code evolves, we need a lot of automation. But at the same time, if you have a fully automatic verifier, you run the risk that in the presence of undecidable verification problems, the verifier might behave unpredictably. For instance, you might do a small change to your specification and it just sort of spins forever. So we want to try to do better than that and provide predictable automation. And our scheme for doing this looks something like that. For dealing with the semantics of C, we want to build on the Cerberus model. For achieving predictable automation, we want to build on the liquid types work, and we want to use separation logic for dealing with these low-level aspects. And then there's some interesting tension between this goal of predictable automation and the complex invariance low-level systems code may rely on, and we'll sort of figure out along the way what we do here. So I'll just sort of start talking a bit about the details and start with the C semantics now. So C is a really complicated language. We've got implementation, defined behaviors, undefined behaviors, implicit integer type coercions, mutable local variables of which you can take the address and pass it around. There's complex control flow, complex variable scoping rules, and underspecified sequencing of memory accesses and a subtle memory object model. So the last two I put to do because those were not handling correctly yet. But the bottom line is dealing with this complexity directly within this type system that we're developing would be both tedious and error-prone. So we're trying to delegate this to Cerberus. So Cerberus by Kayvan, Memarian, and others is a well-validated semantics for C, and it works by elaboration. So given a C program, it translates it to this nicer language called core, and the idea is that this translation makes all the difficulties of C explicit in the produced program. So if you give it this this increment function here, which takes a signed int I, increments it, and returns, that function gets translated to this core function here. And you can ignore the details. I'll just sort of point out three things. The first is, in place of C bounded integers, we've got unbounded mathematical integer types. We have explicit undefined behavior checks in the program, and explicit management of stack variables using create and kill, and their access using loads and stores. So all of this is nice and makes our life easier because it means we can use Cerberus inside the type system. And so CN is effectively a type system for core. So if you give it a C program and some specifications and definitions, we use Cerberus to translate it to a core program. We'll do some core-to-core simplifying rewrites, and then CN type checks the core program. CN is implemented in OCaml, but for constraint solving and basically delegating refinement typing, we interface with C3. We also use that for getting counter models, and so the idea is if you invoke CN on your C program and verification fails, then it gives you a counter example, and we're currently working on improving those. So this gives you a sort of high-level idea of the pipeline. Now I'll just tell you about a couple of points about the type system design. And again, the two main goals here are first handling the complexity of real-world system software and achieving predictable automation. And for achieving predictability, what we want to do is make sure all the SMT constraints we generate are always in a decidable quantifier-free fragment. And we want to do that by building on the liquid types work. So if you take this increment function from before and you run CN on it, it'll complain about some undefined behavior resulting from a signed int overflow. So you can fix this by constraining the inputs and say that you can ask for I to be one less than the maximal representable value to avoid the overflow. And here's another constraint that we're adding to say that the return value is I incremented. So that fixes the problem. That's the user-facing syntax. Internally, CN has types that look more like this. So if we take this information about the signed int I type, this gets translated into this pi binder here for a type variable of mathematical unbounded integer type, together with a range constraint that says it's within this signed int range. Then we do the same for the return type, which turns into this sigma binder for the return value here, again of unbounded integer type, together with a range constraint. And then these user-written specifications turn into corresponding constraint types. Now the type checking against types of this kind is just standard liquid types. So the liquid types people have figured out a scheme for doing refinement typing for this just by translating it to quantifier-free decidable SMT constraints. So we're building on this work, and I won't talk about the details about this here now. But if we apply this scheme to systems programs in general, then we run into a couple of problems. And I'll just sort of step through them and tell you what we do about those. So the obvious first problem is that C functions are stateful. So we want to use some form of substructural types to deal with this. We'd like something more flexible than Rust's ownership type. So in Rust, ownership of memory is closely coupled with the types of the pointers. And here we'd like something more flexible for dealing with low-level systems code and things like pointer aliasing and pointer arithmetic. And so what we do is we borrow resource types from separation logic. So we've got a built-in type that's called owned, it's equivalent to points to, and we have user-defined predicates. And these resource types are first class in the sense that they're types in their own right, rather than something you just sort of stick onto a pointer type. And that's something that's inspired by the L3 type system. So that means we can fairly easily support things like, pointer aliasing like in this example. So here we've got a function f that takes an in pointer p. We're asserting that on function entry we have ownership for p, and it's returned on function exit. Then in the function body we're creating this alias q of p, and then CN is quite happy for p and q to be used interchangeably because it can move around the resource types. The ownership isn't somehow moved out of p when doing this aliasing here. Resources are, well, the use of resources is inferred, except users have to write explicit pack and unpack statements for opening and closing resource predicates. Right. So then the immediate next problem we run into is that for interesting specifications involving resources, we need a way of abstracting over the values of the resources. So we need quantifiers, but we want to guarantee reliable inference, and general quantifiers break reliable inference. So here's an example. You say there exists an x such that p points to x. That's completely fine. It's okay, because if you wanted to type check against this, you could scan your resource context and try come up with a points to fact for p and instantiate the x accordingly. This one is a problem for inference though. So here we say there exists an x such that q points to x. The problem is that this is satisfied by any owned heap cell, and so we can't reliably infer this without doing backtracking for instantiating what this q should be. So we want to rule out this kind of specification. And right, so what's the difference between these two? It has something to do with the modes of the resource arguments. And so the idea is, given a resource predicate, you can partition the arguments into inputs and outputs with the intuition that inputs determine the outputs. So for the example of a points to, if you have p points to x, the pointer p is the input and x, the pointee, is the output, because the pointer uniquely determines the pointee. But you can do that for resource predicates in general. And this is interesting because outputs are uniquely determined by the inputs, it means we can allow quantification over the outputs. Now, this idea of using resource inputs and outputs in inference isn't new. What's new is that we're restricting the expressible specifications to only those that are guaranteed to work well, where we can reliably instantiate these quantifiers. And we do that using a special new syntax that we call resource-led bindings. So we want to only permit quantification over the resource outputs. And we could do that by having some sort of mode check. But what we're doing instead is we're using this resource-led binding syntax. So where in separation logic you'd write there exists an x such that p points to x, we'll write this let binding that says let x equals own p, and this isn't your normal let binding, because it sort of asserts the ownership of p, and at the same time binds the outputs of this resource to x. But it's just equivalent to this. So if it's equivalent, why is it interesting? The interesting thing about it is that this syntactically enforces this mode correctness that we need for reliable inference, and it does that via this familiar concept of variable scoping. So the idea is, if someone writes a specification that wouldn't work reliably, then they would have made a variable scoping error, and we could report it in using that concept rather than some obscure sort of mode discipline concept. Okay. Now, for sort of following through with this scheme, we also have a special syntax for resource predicate definitions, and they end up looking a lot like function definitions. So if you take a standard linked list example and look at the separation logic formula, it would look something like this. I won't have time to talk about the details now. Just in CN, it ends up, the same thing ends up looking like this, and it's equivalent, but basically ends up looking like a function definition and allows us to avoid these quantifiers here. They're eliminated. And curiously, this code also looks a lot like the code you might write for, as a C programmer for traversing a linked list. So that's sort of nice. Okay, and then the third and last problem I'll talk about is that C allows computed access into arrays via pointer arithmetic. And the problem with that is that these computed accesses can be sort of random in the sense that they're not naturally aligned with some nice inductively defined resource predicate. So we want to support that, and we're building on some work for doing iterated separating conjunctions for the Viper verifier here. So maybe I'll skip this example, but the idea is we can compute some. Sorry, we can support some computed access of this kind. Okay. The grammar of C and types we arrive at is something like this, and I won't tell you about the details. The idea is just it doesn't look so bad. It's still a relatively simple grammar of types that we end up with. The paper has some other aspects, like coq export of certain lemma statements that we use in the proofs and some other things. But maybe this gives you a rough idea of what the type system design looks like. So how do we check if it's any good, this type system? The first thing we do is we've got a formalization of key type system aspects. So a formalization of a kernel language that's basically an a-normalized core language together with explicit terms manipulating the resources. And we've got a type system set up as a bidirectional type system and proved soundness of type checking, not inference yet. And then the second thing we do for checking if this type system is any good for real-world systems code is we've done a case study and verified a substantial component of this pKVM hypervisor, namely its allocator. So this allocator is something pKVM uses internally for managing its page table memory. And it's quite tricky for a couple of reasons. And the main one is that it uses some aliasing data structure called the VMem map. So this VMem map holds for each page of allocator memory, the VMem map holds some metadata. And it's defined by this structure page type. So we've got a ref count for each page, an order. The idea is if you have two adjacent pages at the same order, they can be coalesced into a page of a higher order and split again as needed. Then there's a thing called a pool, which we can ignore, and a free list, which is a linked list of free pages at the same order. You have one of those for each order. Now, what's tricky about this is just the VMem map is accessed using two different kinds of pointers. The first is these linked list pointers. But the second one is that every so often the hypervisor is interested in getting the metadata for some physical address phys, or maybe its adjacent page. So then it does some small calculation to go from physical address to, it computes an index into the VMem map to get the metadata. We have to justify the safety of both kinds of accesses, but of course separation logic ownership is unique, so we have to do some work here. What we do is we assert an iterated separating conjunction that holds the ownership for the relevant subrange of this VMem map, all the indices as a sort of flat structure, and then we carry sort of through this invariant that all the linked list pointers are always pointers into this range of into this owned range of the VMem map, and so that allows us to support both kinds of accesses here. It's a bit more complicated than that in practice, but that's roughly the scheme. We've verified this code mostly unchanged and collected a couple of statistics. So it's 364 lines of code, this body allocator that turns it to 6,000 something lines of core. And well, all the things together, we end up with a verification overhead of 5.9 times the code size roughly. Type checking takes 155 seconds, which is sort of not completely terrible given how complex the correctness argument is, but something we'd like to improve on for making the experience more sort of type system-like. Yeah, and that's it. So is it a successful experiment? It's too early to tell. The verification of the body allocator is promising, but we have to try it on more code and see how it goes. And so that's our main plan for future work. Try it on more pieces of pKVM, improve the user experience and the error messages, and see what the Google developers, the people actually writing the code, think about this type system. Thank you.
Okay, we have time for some questions. So please, before asking the question, state your name and institute. So Leonard. There.
Leonard Beringer, Princeton. I was wondering whether you could say a little bit more about advanced features in C, sort of concurrency, function pointers, and also the semantic model underneath.
Yeah, we don't have any of those yet. Simple concurrency shouldn't be so hard to support, but we haven't done it, so we'll see. And relaxed memory concurrency is a whole other story. And so far it's all first order, and we have no support for function pointers at the moment. So our plan is to do something quite low tech, because there is some use of function pointers in pKVM, but we're planning to just sort of annotate a function pointer with the 3 or so instances that this pointer could be instantiated with, and then verify it 3 times, so then we don't have to deal with it really. But maybe there's something better to be done, yeah.
Zhong Shao from Yale University. So you use SMT solver, right, Z3. Will there ever be some kind of a proof object at the end of the day when you...
Sorry, will there ever be a foundational proof is the question?
Yeah, foundational proof object.
Yeah, I mean, that's a good question. We haven't settled on that yet. There's sort of 2 schemes we have in mind. So the refined C people, some of them are in the audience. If you know about refined C, one thing we're considering is sort of maybe making CN do some inference and taking fully type annotated programs, shipping them to refined C, which is foundationally verified. So this is one possible route. And another one is maybe you don't even want to care so much about the C semantics, but check that it holds at the binary level. And you might then want to do some CN scheme in further types, translate them down to the binary and do something there. We haven't settled on the scheme yet, but it would be good to have foundational proof.
Any more questions? See a hand there. Oh,
there's a question here.
Okay,
Also here.
go for it.
I'm Faizan Asrabadi from CISPA in Germany. You do a translation from C to Cerberus, and I'm wondering, do you do the correctness or soundness of your translation? Do you have any proofs?
We have no proof, and there can't be. It's part of the. The question is, Cerberus translates C to core. Is there a soundness argument for this translation? It's trusted, but it's trusted in the sense that it's part of the definition of what we think is C, or what Kayvan thinks is C. So it's an instrument for defining the language, and so we trust it as you would in the case of another language semantics definition.
Okay. Yeah. Thank you.
Okay, let's thank the speaker once more for this talk.